When it comes to searching for alien life, we're left with just two simple possibilities. It's either we are alone in this universe, or we're not. But however the case may be, both are equally terrifying. Let me explain why. Firstly, the thought of being alone in this universe is quite unsettling. It would mean that Earth, with its vast diversity of life forms, is the only place where intelligent beings exist. The implications of this are profound. It would imply that the emergence of intelligent life is an exceedingly rare event, perhaps even a miraculous occurrence. It would also mean that the fate of the entire universe rests solely on our shoulders, as there would be no other civilizations to share in the exploration and understanding of the cosmos. On the other hand, the possibility of not being alone in the universe is equally terrifying, albeit for different reasons. If there are other intelligent civilizations out there, it raises the question of their intentions and capabilities. Are they benevolent, or do they pose a threat? Are they more advanced than us, or are we the more advanced species? And where exactly can we find them? To begin with, I want us to divide our knowledge base into three separate sections. We'll start with what is known to be true today, in 2023, what we assume to be true based on our current knowledge, and what still remains unknown, even with our best available information. Regarding the things we know to be true, this encompasses significant achievements from both the experimental and observational aspects, supported by concrete evidence, as well as theoretical extrapolations from our best theories that explain their necessary consequences. We now have knowledge about the number of stars, how many are similar to the Sun, the ones potentially hosting rocky planets and possibly life, the systems within the observable universe, and those we could observe with advanced technology. It's remarkable that within just about 30 years, we've transitioned from not knowing these answers to having definitive knowledge about them all. Within our own Milky Way, there are somewhere around 400 billion stars, but the Milky Way itself is a particularly large, evolved, late-time galaxy compared to the average galaxy in the universe. We can analyze the metallicity of stars in the Milky Way, which is the proportion of heavy elements within a star compared to hydrogen or helium. This helps us understand the relationship between a star's metallicity and its likelihood of having planets. We can also categorize stars by their mass and spectral type to determine what fraction of them could possibly host Earth-like planets. When we say Earth-like, we mean planets that are rocky, similar in mass and size to Earth, located at a distance from their parent star that allows for similar energy receipt as Earth gets from the Sun. Currently, this is the extent of what we can measure. Lastly, we can use our understanding of star formation in the universe and our observations of galaxies, along with theoretical predictions for galaxies that are challenging to directly study due to their faintness, low mass, proximity to larger galaxies, or extreme distance, to estimate the number of potentially habitable worlds within the observable universe. All of this information falls under the category of what we definitely know to be true as at 2023. In our visible universe, there are approximately 2.2 sextillion stars, which is about 2.2 followed by 20 zeros. These stars come in various types, sizes, and ages. Out of all these stars, only about 4%, or roughly 8 followed by 19 zeros, are observable from Earth. Most of the stars were formed in galaxies we can only see from their early stages. Among the stars, around 3 to 5% are of the same type, G-type, as our Sun. Approximately 15 to 20% are cooler and less massive, K-type, and the majority, about 75 to 80%, are the coolest and least massive red dwarf stars, M-type. Only around 2% are bright, blue, and have a short lifespan. For stars to potentially have rocky planets, they need to contain a sufficient amount of heavy elements. On average, this cutoff is around 25% of the heavy elements in our Sun. Stars with more than this level account for about 98% of known planets, while those with less make up only about 2% of all known planets. Even with these criteria in place, we still have an enormous number of planets that could be considered as potential candidates for supporting some form of life in the universe. There might be around 10 to the power of 19, or possibly more according to some estimates, such planets that could be observed from Earth, assuming we had incredibly advanced technology but remained within the confines of the laws of physics. Now, to move forward, scientists must rely on assumptions because we have only one example of a known world with life: Earth. Beyond this point, we venture into the unknown, and it's essential to be transparent about the assumptions we are making. We assume that life originated through natural processes from non-life, and any planet with the right chemical ingredients and environmental conditions, whether similar to Earth or different, can be considered a potential candidate for life. We assume that the fundamental laws of physics we observe on Earth and within our solar system are the same laws governing the entire universe. We assume that life is defined as an entity capable of extracting energy from its environment, utilizing that energy for life processes, and either reproducing or producing related offspring in some manner. Although these are common assumptions among biologists, astrobiologists, and most scientists who study the origin of life, there are often people who make different assumptions about one or more of these, so it's important to state the naturalistic position explicitly. Additionally, there are also cosmological assumptions to consider. We assume that the unobservable part of the universe follows the same fundamental principles and shares similar or identical conditions with the part of the universe we are acquainted with. We also assume that the process leading to the hot Big Bang, known as cosmic inflation, not only resulted in a hot Big Bang on a much grander scale than our observable universe, but also aligns with the predictions of inflation and the constraints set by our observations of the observable part of the universe. There is an unobservable universe that goes on for at least 400 times the radius and 64 million times the volume of our presently observable universe. It's filled with the same sort of stuff that comes to exist in our universe, including the ingredients for galaxies, stars, planets, and life. And there may be an inflationary multiverse separating different pockets of space or different observable universes from one another. This should create, overall, an enormous set of disconnected universes that are not only beyond our own observable universe, but beyond our unobservable universe as well. However, it is only the portion of our universe that's within our light cone, which is where we can potentially receive signals that were emitted since the Big Bang, that we consider as detectable extraterrestrial life. Unfortunately, we now move from the known and the well-assumed into the realm of speculation. Science has yet to answer these challenging questions. What is the mechanism by which life originates from non-life here on Earth? What are the various mechanisms by which life can arise, and how common are these mechanisms? When life emerges, how frequently does it endure for long periods versus getting wiped out shortly after appearing on a world? In cases where life arises and endures, how often and after does it evolve into what we'd call complex and differentiated life? Once life becomes complex and differentiated, how frequently does it evolve into intelligent and/or technologically advanced forms? And how long do species that capture our interest in that sense persist? Regrettably, we lack any evidence that provides answers to these questions. We must find answers to all of these questions before we can address the fundamental question: could we genuinely be alone? However, our ignorance has never stopped us from what we'd call making healthy speculations, and we won't let our lack of concrete knowledge stop us here. Currently, the leading theory regarding the origin of life from non-life involves a process known as peptide RNA coevolution. The concept revolves around the notion that a collection of amino acids, the fundamental building blocks of proteins, spontaneously formed in a watery environment in the presence of a natural energy source. This theory gains credibility due to the abundant presence of both water and various amino acids in objects like protoplanetesimals, which are remnants from the formation of our solar system, such as asteroids and comets. While there are only approximately 20 amino acids, all with the same handedness or chirality, involved in life processes on Earth, icy and rocky celestial bodies contain more than 80 amino acids with various chiralities. When these amino acids combine to create peptides or proteins, these new molecules can carry out metabolic functions. Introducing ions to a peptide can make it function as an enzyme. By connecting some form of nucleic acid, whether it's based on ribose sugars, RNA, peptides, PNA, or other xeno, meaning stranger in Greek nucleic acids, XNA, you can bestow upon them the capacity for reproduction. Unfortunately, we must now transition into the realm of complete speculation, which I would consider to be rather speculative if we wish to calculate probabilities. Currently, there is no scientific foundation for ascribing any probability or likelihood to the following: life emerging from non-life, life persisting for billions of years or longer on a planet, life evolving into complex and differentiated forms. Complex and differentiated life evolving into intelligent and potentially technologically advanced entities. Our only evidence for any of these processes comes from Earth. On our planet, life emerged from non-life relatively early, no later than 3.8 billion years ago, has been thriving ever since, became complex and differentiated at least around 600 to 700 million years ago, and even evolved into intelligent beings, such as humanity. If each step is reasonably likely, let's say with a 1 to 10% chance of happening on candidate planets, then there could be anywhere from 100 billion to trillions of planets within our observable reach that, at some point, develop intelligent life. On the other hand, if one or more of these steps are quite unlikely, let's say with a 1 in a billion chance, it's plausible that, in the context of intelligent life, we might indeed be alone when it comes to reaching and discovering such a civilization. While our primary interest may lie in discovering intelligent and technologically advanced alien species, a worthwhile scientific pursuit, it's crucial not to limit our search to what we hope to find the most. If we were to encounter a planet where the most intelligent life forms resembled dolphins, dogs, alligators, or even spiders, we would not only be thrilled, but would also make every effort to understand and communicate with this unfamiliar intelligence. Even if all we discovered was a world with microbial life, or even simpler organisms, a scenario scientists anticipate to be the most common on inhabited planets, we would learn that Earth is not unique and that life exists elsewhere in the universe. As long as we remain the only known example of life, we could consider ourselves exceptionally fortunate in the cosmic lottery of biology. However, if we were to find a second instance of life, it would not only provide reason to believe that there are many more, but also enable us to begin estimating the prevalence of inhabited worlds. Currently, we have identified over 5,000 exoplanets, but with cutting-edge observatories like the James Webb Space Telescope and ambitious projects like Starshade on the horizon, this number is expected to increase significantly. These advanced tools will enable us to better analyze exoplanets and assess their potential habitability. The presence of certain characteristics, such as seasonal changes, liquid water on the surface, or specific organic compounds, might point to the possibility of life. However, even if we find a planet with promising conditions, that alone does not guarantee the presence of life. Life might never have emerged on that world, or if it did, it could have been wiped out by catastrophic events like massive impacts or nearby supernova explosions. Planets that show signs of potential habitability and harbor the necessary conditions for life to emerge becomes one of the prime suspects for study. Specific organic compounds like chlorophyll, which are predominantly produced by living organisms, could be key indicators. Additionally, signatures of large biomass, such as those found in rainforests, could create discernible changes in environmental parameters like temperature or cloud distribution, setting them apart from barren landscapes of rocks and sand. In our search for life, we must remain open to the possibility of encountering various forms of intelligence and evolution. It's essential to remember that life's timeline on Earth spans billions of years, from microbial life existing for roughly 4 billion years to recent technologically advanced life emerging only in the last 100 years. Considering the vastness of the universe and the diverse array of conditions on other planets, it is plausible that we may discover life forms at different stages of evolution. Some might be in their early stages of development, akin to the ancient microbial life that once dominated Earth, while others could be on a path toward advanced civilizations, much like our own relatively recent technological achievements. But you see, as humans, our understanding of intelligence, civilization, and communication is deeply rooted in our own experiences and societal norms. However, projecting our behaviors onto potential alien life forms might lead us astray in our quest to decipher the paradox. Imagine civilizations that have evolved on distant planets, under entirely different conditions and evolutionary pathways. These alien societies might possess cognitive abilities, values, and methods of communication far beyond our current comprehension. Their understanding of the universe, science, and technology could be vastly different from ours, making their approach to space exploration and communication unconventional by our standards. While we search for extraterrestrial intelligence through radio signals and other technological means, advanced alien beings might have developed alternative forms of communication that we have not yet fathomed. Their methods could transcend our comprehension, existing on planes beyond our current grasp of physics and biology. Moreover, the very concept of intelligence might vary significantly among different species. Intelligence on Earth can manifest in various ways, from human cognitive abilities to the sophisticated social structures of certain animal species. Similarly, alien intelligence could encompass an astonishing array of forms, making it challenging for us to recognize and understand. Furthermore, the Fermi paradox relies on the assumption that advanced alien civilizations would exhibit expansionist tendencies, similar to our historical exploration and colonization drives. However, this assumption could be overly anthropocentric, as the motives driving an extraterrestrial civilization might be entirely different from our own. Consider the possibility that some advanced alien civilizations prioritize harmony with their environments and seek to preserve their own planets rather than colonizing others. Perhaps they have found a sustainable balance and prefer to remain hidden from other civilizations, avoiding potential conflicts that could arise from interstellar contact. In essence, this solution to the Fermi paradox encourages us to broaden our horizons and remain humble in the face of the unknown. We must embrace the diversity of potential alien behaviors, acknowledging that our understanding of intelligence and societal behavior might be just one of countless possibilities in the vast cosmic landscape. Studying the patterns of human civilizations, scientists observed that many rose to greatness but eventually faced collapse. Similarly, when investigating the history of large cities, they noticed that most reached a certain point of growth and development, only to experience a subsequent decline. These findings served as the foundation for a hypothesis regarding the fate of any alien space civilizations. The hypothesis proposed two possible scenarios for these extraterrestrial civilizations. In the first scenario, a civilization would reach a critical point where it became aware of its exponential growth and recognized the dangers of expanding too far and too fast. In response, they would choose to halt their interstellar travels and refrain from further colonizing other worlds. In the second scenario, a civilization might fail to recognize the impending consequences of their expansion and continue their encroachment until a point of no return, leading to their eventual collapse. Remarkably, from our perspective, both scenarios would yield the same result: aliens not visiting us or revealing evidence of their existence. The distance between their civilization and ours would simply be too vast for meaningful contact or detection. The researchers dubbed this hypothesis superlinear scaling. According to this concept, a civilization grows exponentially, spreading out and colonizing other worlds, fueled by its increasing energy demands. However, as they venture further and expand, they may encounter challenges in sustaining the immense energy requirements of such vast colonization efforts. Unless they take timely action to address these issues, they would eventually reach a point of no return, a singularity, where the collapse of their civilization becomes unavoidable. Interestingly, the researchers highlighted that if these alien civilizations were closer to us, we would likely detect signs of their existence, especially if they were on the brink of collapse. At this stage, they would be emitting enormous amounts of energy, making their presence conspicuous. This hypothesis is particularly intriguing when considering other assumptions proposed in the search for alien life. The first assumption posits that advanced civilizations may not prioritize exploring planets teeming with life, especially those in the early stages of development. It is possible that these civilizations have encountered numerous biotic worlds throughout the galaxy, but the allocation of resources to investigate each one may not be practical. Moreover, attempting to communicate with primitive life forms might not yield meaningful outcomes, rendering such efforts less appealing to advanced beings. On the other hand, the second assumption highlights that once a planet develops intelligent life, it becomes far more intriguing to advanced civilizations. The rarity of intelligent life in the galaxy makes each instance of it noteworthy. Detecting signs of intelligence from afar, similar to our SETI project, becomes a priority for these civilizations. Considering the Earth's perspective, the most detectable signs of our intelligence would be the radio signals transmitted over the past century. these signals could have potentially reached around 1,300 star systems within a radius of 50 light-years out of the 100 billion to 400 billion star systems in the Milky Way. However, the radio signals, unintentional techno-signatures, would become indistinguishable from background noise after traveling for about a light-year. With this in mind, the proposed solution suggests that even in the 1,300 star systems that could have received our signals, there is a significant chance that they wouldn't have been able to detect our unintentional transmissions. Moreover, if non-intelligent life is abundant in the galaxy, advanced civilizations might not see a reason to expend resources trying to contact potentially non-intelligent worlds. Therefore, the silence from extraterrestrial civilizations could be attributed to their lack of evidence of intelligent life on Earth. The vastness of the galaxy and the challenges of detecting intelligent civilizations from afar make it plausible that advanced alien beings have not yet noticed any indication of our intelligence. And now, what are the possible solutions to this paradox? One argues no superintelligent beings exist, while the other suggests less concrete reasons for the lack of contact. The first is the theory of the Great Filter. This solution suggests that from the very beginning of life's emergence, through the intricate stages of development, all the way up to achieving highly advanced civilizations on the Kardashev scale, there exists a significant obstacle that hinders the progress of life, making the existence of detectable extraterrestrial life extremely rare. The idea was first proposed in an online essay titled "The Great Filter, Are We Almost Past It?" written by economist Robin Hanson. With no evidence of intelligent life in places other than the Earth, it appears that the process of starting with a star and ending with advanced explosive lasting life must be unlikely. This implies that at least one step in this process must be improbable. Hanson's list outlines a comprehensive evolutionary path comprising 9 crucial steps that could lead to the eventual colonization of the observable universe, which are the right star system, including organics and potentially habitable planets; reproductive molecules, simple, prokaryotic, single-cell life; complex, eukaryotic, single-cell life; sexual reproduction, multi-cell life; tool-using animals with intelligence; a civilization advancing toward the potential for a colonization explosion, where we are now; and colonization explosion. According to the Great Filter hypothesis, if this list were complete, at least one of these steps must be highly improbable. If the improbable step lies in the past, it suggests that humanity's chances of reaching step 9, interstellar colonization, are grim. Conversely, if the preceding steps are likely, then numerous civilizations should have progressed to a level akin to our own. Yet, we find no evidence of step 9 being attained, as the Milky Way remains devoid of colonies. Hence, step 9 may be the elusive and improbable milestone that hinders civilizations from flourishing. Potential obstacles preventing us from reaching step 9 could include catastrophic events, underestimation of the impact of technological procrastination as our reliance on technology grows, or resource depletion rendering the step impossible due to the exhaustion of available resources, such as highly constrained energy sources. Therefore, by this line of reasoning, the discovery of multicellular life on Mars would be disheartening. Its existence would imply that steps 2 to 6 are relatively easy to achieve, thus directing attention to steps 1, 7, and 8, or perhaps an unknown step as the true stumbling block. Although steps 1 to 8 have indeed transpired on Earth, each one of them could still be considered unlikely. If the first 7 steps are necessary prerequisites for estimating probabilities based on our local environment, then an observer biased by the anthropic principle can glean nothing definitive about the general likelihood from its predetermined surroundings. Everything I just said might not make sense to you. Let me take another approach to this theory. Think of it like some kind of cosmic video game where you have to pass through various levels to get to the final level. The Great Filter is like a level that all civilizations have to pass through, and it's really hard. Maybe it's a technological challenge like developing interstellar travel or creating artificial intelligence. Or maybe it's a societal challenge, like avoiding catastrophic wars or solving problems like climate change. The idea is that many civilizations might not make it through the Great Filter. They might get stuck at some point, unable to progress any further. Maybe they never develop the technology they need. Or maybe they destroy themselves in a catastrophic event before they get the chance. Our planet has successfully weathered numerous challenges in the form of mass extinction events, serving as filters for the evolution of life. Take, for instance, the Permian-Triassic extinction, also known as the Great Dying, which occurred approximately 250 million years ago. This cataclysmic event came close to obliterating life on Earth, devastating about 96% of marine species and 70% of land-dwelling organisms. Although the precise cause of the Great Dying remains a mystery, some scientists theorize that a combination of rising temperatures and declining oxygen levels played a role. However, it is crucial to note that these previous filters, manifested as natural extinction events, arose as part of our planet's and solar system's evolutionary processes. They were outcomes of volcanic eruptions, asteroid impacts, and other natural phenomena. Yet, humanity finds itself potentially confronting a great filter of our own making. This filter could materialize in the form of imminent threats, such as climate change, nuclear warfare, or other catastrophes induced by human actions. Such dangers have the potential to impede our civilization's progress, preventing us from reaching the stage where communication with extraterrestrial life becomes possible. So the search for alien life is a bit like a cosmic game of hide and seek. We're looking for signs of other civilizations that have made it through the Great Filter, but we don't know how many have actually made it. Rare Earth, proposed by Peter Ward and Ron Brownlee, suggests that the unique combination of geological and environmental conditions on Earth makes the evolution of complex and intelligent life exceedingly rare in the universe. They argue that while microbial life might emerge on some planets, the development of sophisticated life forms is highly unlikely. However, a counter-hypothesis called cosmic zoo, proposed by William Baines and his colleague, takes a different stance. They believe that just as there are various styles of music, there are multiple ways for life to evolve from simple microbes to complex macroscopic creatures similar to animals and plants. The cosmic zoo hypothesis suggests that once life arises on a planet, it has the potential to evolve into diverse and substantial forms, provided the planet remains habitable long enough. While the debate continues, two critical caveats exist. Firstly, the origin of life on Earth, despite not being considered a unique event, remains shrouded in mystery, leaving room for the possibility that Earth's conditions are indeed rare. Secondly, the evolution of technologically advanced life, exemplified by humans on Earth, seems to have occurred just once. This uniqueness makes it challenging to estimate how common such advanced civilizations might be on other worlds. To determine which hypothesis holds true, scientists turn their attention to our own solar system. Several planets and moons, including Mars, Europa, Enceladus, Titan, and Venus, present opportunities to search for microbial life. The discovery of independently originated microbes in these locations would suggest that life is widespread in the cosmos, providing a significant data point. However, to differentiate between rare Earth and cosmic zoo, the quest for complex macroscopic life demands exploration beyond our solar system. Europa, with its subsurface ocean beneath an icy crust, offers a tantalizing possibility for such life, as hydrothermal vents on its ocean floor could potentially support animal life. Nevertheless, the search for intelligent life necessitates looking further afield, to exoplanets orbiting stars beyond our sun. In a paper called Eternal Inflation and Its Implications, Alan Guth, a theoretical physicist, used the physics of inflation to elegantly show that each universe, and by the way, we're assuming the existence of an infinite number of universes, likely has only one advanced civilization. Here's how the argument goes. According to Guth, cosmic inflation spawns an infinite number of pocket universes at an extraordinary rate. In fact, every second, the number of pocket universes increases by a factor of 10 to power 37. Therefore, Guth argues, we can assume that young pocket universes vastly outnumber older universes. In other words, the average universe is remarkably young. Guth then postulates that there is a minimum time, let's call it T, required for intelligent life like ours to develop. Because we've already developed, we know that the age of our universe is greater than or equal to T. Let's imagine there is another civilization in our universe more advanced than ours, and for the sake of argument, let's assume that it is 1 second more advanced. If the minimum time for our civilization to develop is t, the minimum time for this more advanced civilization to develop is greater than or equal to t plus 1 second. Because the number of universes that satisfy the t requirement is 10 to the power of 37 times the number of universes that satisfy the t plus 1 second requirement, and because we know only that we live in a universe that satisfies the t requirement, it is extremely unlikely that our universe also satisfies the t plus 1 second requirement. It's unlikely, therefore, that there is an alien civilization in our own universe even 1 second more advanced than ours. Everything I just said might be a little bit confusing. Let me take another approach. Imagine the universe as a vast and diverse canvas where countless paintings of reality come to life. Each painting represents a unique world with its own story and inhabitants. Now, in this cosmic art gallery, new paintings are continuously being added to the gallery, appearing like magic with each passing moment. However, most of these new paintings are still fresh and not fully developed. Guth believes that for intelligent life to emerge and flourish within a painting, it requires a certain amount of time, like a masterpiece slowly taking shape. So, in some paintings, life might just be taking its first strokes, while in others it may have had more time to evolve and grow. Now, here's where it gets intriguing. Imagine there's another painting nearby where life is slightly more advanced than in ours, just a tiny step ahead. According to Guth's theory, the number of paintings with life at our current level is immensely greater than the ones where civilizations are just a tiny bit more advanced. Because the gallery is filled with countless paintings at our level, it becomes highly unlikely that we would find one where a civilization is only a small increment ahead. So it's quite possible that our painting holds one of the most advanced civilizations in this grand cosmic artistry. Guth's idea can be illustrated in this idea of multiple paintings and unique civilizations, adding a captivating perspective to our understanding of the universe. It prompts us to ponder the diversity of life and intelligence across this cosmic gallery, leaving us in awe of the infinite possibilities that await beyond our own canvas. Nick Bostrom, a philosopher at Oxford and director of the Future of Humanity Institute, developed an argument in a paper called "Are You Living in a Computer Simulation?" He argues that at least one of the following 3 statements must be true. It's either humans are likely to go extinct before they are post-human and able to create entirely simulated realities. A post-human civilization with the ability to run such a simulation would likely not run many simulations. We are currently living in a computer simulation. Now, using ingenious logic and mathematical reasoning, Bostrom puts forth a thought-provoking conclusion. He argues that unless we are already residing in a simulation, the belief that we will eventually become post-humans capable of running ancestor simulations is likely false. Consider the idea of how such a simulation could be created. Speculations from writers suggest that an advanced Type 2 or 3 civilization might construct a colossal computer system known as a matryoshka brain. This unfathomably massive system would harness the entire energy output of a star, utilizing a Dyson sphere, which is a shell surrounding the star to capture all its energy. Mathematicians have pondered the capabilities of a matryoshka brain and calculated that it could possess enough computational power to create an entire simulated universe, where we, among countless other beings, could be living unknowingly. Remarkably, this concept doesn't seem to violate any known laws of physics. It sparks a fascinating exploration of the nature of reality, the potential existence of advanced civilizations, and the profound implications of our place in a vast simulated universe. If we entertain the notion that we are living in a simulated universe, created by a highly advanced civilization with a matryoshka brain or a similar vast computational system, then the question of the existence of extraterrestrial life takes on a new perspective. In this simulated reality, the beings responsible for creating the simulation could have engineered various scenarios and worlds, including ones with intelligent life forms like us. These simulated beings, including potential aliens, might be part of the design of this grand cosmic experiment. Furthermore, if the creators of the simulation possess the ability to manipulate the parameters and variables of the simulated universe, they could introduce diverse life forms and civilizations, including those of extraterrestrial origin. As a result, the presence of aliens within this simulated reality becomes a plausible possibility. From our standpoint as simulated beings, the search for extraterrestrial life might lead to intriguing questions. Are other intelligent civilizations we encounter real entities living in their own separate simulations, or are they simulated entities like us? Moreover, if we are part of a simulated universe, the Fermi paradox could be reevaluated. Perhaps the silence from alien civilizations is a deliberate design of the simulation, or the result of the limitations imposed by the creators. In the realm of quantum mechanics, entanglement allows two particles to become correlated in such a way that the state of one particle is instantly connected to the state of another, regardless of the distance between them. Superposition, on the other hand, allows quantum particles to exist in multiple states simultaneously. Imagine a scenario where advanced alien civilizations encode their communications and energy emissions using quantum entangled particles and superposition states. By doing so, they can create encrypted signals that appear as random noise or background radiation to less advanced civilizations' detection technologies. To an outsider, it would seem as if these advanced civilizations do not emit any detectable signals or energy signatures, leading us to perceive them as silent or non-existent. In reality, they are actively communicating and functioning within the universe, but their quantum information hiding techniques make them invisible to conventional detection methods. Furthermore, these civilizations might have developed quantum cloaking technologies that render their spacecraft and installations non-transparent to electromagnetic waves. This would enable them to move through space undetected, making it challenging for us to observe their presence. Water, light, heat, organic molecules, and the building blocks for life are indeed abundant throughout the universe. However, we have yet to encounter any form of extraterrestrial life. As far as our concrete evidence goes, Earth might be the sole abode of life in the entire universe. If this notion appears pessimistic to you or aligns with Carl Sagan's characterization of it as an awful waste of space, you're not alone. Originally, there was no straightforward method for estimating the number of technologically advanced civilizations, but Frank Drake came up with a brilliant approach. He devised an equation that involved multiple parameters that could be estimated and then multiplied together. If your estimates were accurate, the equation would yield an accurate count of the technologically advanced civilizations in our galaxy with which humanity could potentially communicate at any given time. This concept was ingenious, but as our understanding of the universe has expanded, the Drake equation has become less useful. In its current form, the Drake equation might even be less effective, but we now possess sufficient knowledge about the universe to develop an even more improved framework. The Drake equation, in particular, aimed to calculate the number of civilizations, n, present within our galaxy at any given time. It was expressed as the product of 7 distinct unknown factors, spanning the realms of astronomy, geology, biology, and anthropology. These elements build upon one another, and they are as follows. R. The average rate of star formation. FP, the fraction of stars that possess planets. NE, the average number of stars with planets that have planets capable of supporting life. FL, the fraction of these life-sustaining planets where life has emerged. FI, the fraction of life-bearing planets that have developed intelligent life. FC, the fraction of these intelligent civilizations that are capable of communicating across interstellar space. L, the length of time over which such a civilization can transmit signals or listen for extraterrestrial messages. Multiply these numbers all together, in theory, and that will give you the number of technologically advanced broadcasting civilizations we have in the Milky Way today. However, there are significant flaws in this framework. It relies on several unspoken assumptions that do not align with reality, rendering it less useful in the modern context. These issues include the fact that the equation was written before the Big Bang was validated and the steady-state model was disfavored. The equation assumes that only one planet per star system could support life, that intelligent, technologically advanced life will never spread to other worlds, and that broadcasting and listening for radio signals is the method by which an intelligent species would choose to communicate across interstellar space. In particular, the last assumption drove the motivation behind SETI, the search for extraterrestrial intelligence using radio dishes, which of course has not yielded any positive results. Nonetheless, the absence of evidence doesn't rule out the possibility of other worlds hosting intelligent life. Despite our uncertainties regarding what's out there and the methods they might use to search for or contact us, the existence of intelligent, communicative, or spacefaring extraterrestrials remains a topic of immense interest to scientists and all of humanity. While many aspects of the Drake equation may be problematic and fraught with significant uncertainties, it's now 2023, and our understanding of our galaxy and the universe has expanded significantly since 1961. This prompts us to explore a more refined approach. NS, the number of stars in our galaxy. Why estimate the rate of star formation when we can simply count the stars we have today? We possess detailed knowledge about our galaxy's size, thickness, central bulge dimensions, and mass distribution. Through extensive surveys that observe the entire sky and focus intensely on narrow regions, we can state that there are between 200 and 400 billion stars in our galaxy. An uncertainty of just a factor of 2 is quite acceptable, and it indicates an optimistic starting point. Each star represents a potential opportunity for life. Let's choose the higher figure in this range. FP, the fraction of stars with planets. We can retain this parameter from the original Drake equation, but in the aftermath of Kepler, it isn't all that interesting. Why? Because it's essentially close to 100%. Based on the extensive surveys of stars and the knowledge we've gained, the fraction of stars with planets in orbit around them is estimated to be at least around 80%. To put it simply, stating that the fraction of stars with planets equals 1 is a clear win for the optimists. FH, the fraction of stars with the right conditions for habitability. This is where it gets more intriguing. Among the various classes of stars, how many have planets suitable for life? A star similar to our Sun, with the same mass, radius, and lifetime, could indeed host life, as evidenced by our own existence. However, what about more massive stars? Eventually, they may burn through their fuel too quickly, preventing the emergence of intelligent life. Conversely, lower mass stars might be too unstable, emitting flares that strip away a planet's atmosphere or producing insufficient ultraviolet light for life to thrive. We may also consider whether there are adequate heavy elements to support life on a planet, or whether the environment in a particular region of the galaxy is too chaotic. While there may be unknowns, it's reasonable to suggest that at least a quarter or 25% of stars in our galaxy have the potential to host habitable planets. NP, the number of worlds around habitable stars with the right conditions for life. We've gained substantial knowledge from our studies of exoplanets, but numerous questions remain. What defines a world as habitable? In the early solar system, Venus, Earth, and Mars had similar conditions. In the outer solar system, worlds like Enceladus and Europa, boasting subsurface oceans, could potentially harbor underwater life. In systems with gas giants positioned similarly to Earth, large moons might witness the emergence of life. While there are significant uncertainties, it's reasonable to estimate that, on average, among stars capable of hosting a potentially habitable world, there's one world that stands out as having the most favorable conditions for life. That's the world of greatest interest, so we'll set NP equals sign 1. At this juncture, we can multiply the first 4 numbers together to estimate the number of worlds with favorable conditions for life within our galaxy, 100 billion. This is a promising beginning. FL, the fraction of these worlds where life arises. Among all the potentially habitable worlds, how many take that extraordinary initial step, where life emerges from non-life? Or if primitive life originates in interstellar space, how many worlds witness life taking root on their surfaces, in their oceans, or in their atmospheres? We don't even have the answer for our own solar system, where it's conceivable that life arose on as many as 8 other worlds at some point. The prevalence of life remains uncertain. Optimistically, it might have a 10% chance of emerging from non-life. On the other hand, it could be exceedingly rare, with odds as low as 1 in a million or worse. The uncertainties here are substantial, and any number one selects is as speculative as any other. In the future, we will likely gain the capability to conduct our initial tests. If we assume there's a 1 in 10,000 chance that a potentially habitable world possesses life, a guess as good as any, this implies there are 10 million worlds in the Milky Way where life exists. FX, the fraction of life-having worlds with complex, differentiated organisms. Attempting to classify life as intelligent or not is a matter of debate, even among the top scientists. The categorization of dolphins, great apes, octopi, and various other organisms as intelligent or not remains a subject of ongoing discussion. However, one aspect everyone agrees on is whether an organism is complex and differentiated. Since Earth is our sole laboratory for this type of development, let's take an optimistic approach in the absence of evidence and assume a 1 in 1,000 chance that a world starting with a primitive, replicating, information encoding form of life can eventually lead to something resembling the Cambrian explosion. This estimation suggests there are 10,000 worlds in the Milky Way teeming with diverse, multicellular, highly differentiated forms of life. Given the vast distances between stars, it's likely that another planet where this has occurred is only a few hundred light-years away. AFT, the fraction of those worlds that presently host a scientifically, technologically advanced civilization. This question surpasses the inquiries of the Drake equation. It matters less whether this is the first or 10th time a technologically advanced civilization has emerged. It's not crucial whether they employ radio waves, whether they face self-destruction or self-extinction, or whether they harbor aspirations for interstellar travel. The primary concern is whether extraterrestrial intelligence matches our own in terms of scientific and technological advancement. There's no evidence for such civilizations beyond Earth, leaving a wide range of possibilities. The likelihood could be relatively high, such as 1% of these worlds reaching the stage, or it could be a highly improbable coincidence that humanity even emerged, with odds closer to 1 in a billion. Even with 10,000 such worlds in the Milky Way, under these estimates, there's only about a 10% chance that another scientifically, technologically advanced civilization coexists with us. But with all that said, it's those last three numbers, FL, FX, and FT, that have such large uncertainties that make accurate estimates an impossibility right now. Knowing how many worlds there are out there in the Milky Way with life on them, and finding even one, would have tremendous implications for our existence and for understanding our place in the universe. Taking even the next step and learning that there were complex, differentiated, large organisms on a world, like we have with the fungal, animal, and plant kingdoms on Earth, would revolutionize what's possible. And finally, the chance we'd have to have communication, visitation, and a knowledge exchange with a scientifically or technologically advanced alien species would forever alter the course of humanity. It's all possible, but there's so much more we need to know if we ever want to find out. We must take these steps. The rewards are too great if there's even a chance of learning these answers. Many of us can imagine two different futures unfolding for the enterprise of human civilization. A future where we engage in internal conflicts, quarreling over the planet's finite resources, succumbing to ideologically motivated conflicts, and ultimately sealing our own destruction. If we never discover life beyond Earth, if we never encounter others with whom to communicate, share knowledge and culture, and who offer us hope for a future among the stars, perhaps the most probable outcome indeed will be our own extinction. But there's another possible outcome for humanity. A future where we come together collectively to face the gargantuan challenges facing humans, the environment, planet Earth, and our long-term future. Perhaps the discovery of life beyond Earth, and potentially of one or more intelligent, spacefaring extraterrestrial civilizations, might give us not only the guidance and knowledge we need to survive our growing pains, but something far grander than any terrestrial achievements to hope for. Until that day arrives, we must make do with the knowledge that, at present, we have only one another to extend our kindness and compassion to. And that's it for the video. Thanks for watching, and make sure you subscribe for more videos.